Here we go. All right, we're starting a new type of function today. We're starting. We just finished polynomials, right? Polynomials are the easiest types of functions out there. And next, we're stepping up to the next type of function that grows a little bit faster, that gets smaller a little bit faster. They're called exponentials, and then their step cousins, logistic functions. Logistic functions are like modified exponentials. But you've probably heard the word exponentially used as an adverb. Let me write that word down. Exponentially. You've probably heard that word used on television when people were describing how fast something grew, right? Can anyone confirm that? Like you've heard, like sports announcers, like it was growing exponentially, or something like that, right? Y'all have heard it, okay? And what usually when that's used as an adverb, they use that as an adverb. They don't use it as a mathematical term. They use it more as just a linguistic term to describe something that grows how? Fast. They like to use the word exponentially because it punctuates the fact that the thing was growing very, very rapidly, right? But mathematically, there are things that grow very, very rapidly that aren't exponential. For instance, if we look at x to the fifth, does that grow rapidly? Well, what does the graph look like of x to the fifth? It looks like x to the third, but it's flatter here, and it looks like that. Does this not grow rapidly as x goes to infinity? The y's also go to infinity, and they go to infinity quite rapidly, don't they? But you never hear someone say on TV, well, it was growing quintically, right? No one ever says it was growing cubically or quadratically or quintically. You don't hear those used as adverbs, right? So exponentially is used to describe something that grows very, very fast. Polynomials can grow very, very fast, but exponentials actually do grow faster for large values of x. They are one rung up on the growth scale, okay, from polynomials. So that's why people say, that's why they ring the freaking doorbell. There's a doorbell. So that is the reason people say that it grows exponentially, because they do know to some extent that exponentials grow faster than polynomials. Okay? But what actually quantifies and not qualifies, what actually quantifies exponential growth? In other words, how can we determine that something is actually growing exponentially versus polynomially? The degree? Well, the equation is going to look differently, right? This x to the fifth is not an exponential function, is it? It's a polynomial function because it has a variable as a base and it has a nice little whole number as an exponent. So if we knew what the equation was that was describing the growth, we could probably say, hey, that's not a polynomial, maybe it's exponential, right? But we could also qualify it by using our intuitive definition, which I'm going to give to you right now, okay? Here's the intuitive definition of exponential growth. If something gets bigger, and it can also get smaller exponentially, we call that exponential decay. All right, getting smaller. Here's what it says. A quantity that increases or decreases exponentially will grow at a rate that is directly proportional to the current amount. Directly proportional to the current amount. What does that mean? The more you have, the more it grows, right? That's what it means to be directly proportional to its current amount. It grows at a rate that's proportional to its current amount. So I say that right here. The more you have, the more you gain. Or if you're getting smaller, the less you have, the less you lose. Okay? That's what it means to decay exponentially. The more you have, the more you gain. That is the intuitive definition of exponential growth. The more you have, the more you gain. The more you have, the more you gain. Can you remember that? The more you have, the more you gain. Okay, now on example one, let's think of some real life things that get bigger rapidly. Go. Pufferfish. What do you mean? How, like they expand out? Okay, let's talk about it. A pufferfish gets scared and it puffs up real fast, right? Is it exponentially fast? Does it fit this criteria? The more it has, the more it gained. What would we be talking about? The more fright it has, the bigger it gets faster. You think it expands more slowly if it's less afraid? It's like, oh, this is just a chill situation. This is like, I'll just inflate real slowly here. Shark! Maybe so, maybe not. I've never seen a pufferfish inflate slowly.
You've never seen it not that scared.
We've never seen it not that scared. Pufferfish are just scaredy cats. They're scaredy fish. I'm not sure if that's going to qualify based on fear, but maybe on the expansion, its ability to expand. The more it has expanded, the faster it's going to expand. Does that make sense?
Yeah.
The more that it has expanded, the faster it's going to expand. Is that true? That means that it starts to expand. The more it has, the faster it expands. That means that it's going to be accelerating its expansion. That means it might pop, right? That means the bigger it is, the faster it's expanding. Is that true? I think the reverse is true. The bigger it is, the more slowly it's expanding because it's reaching its capacity, right? Think about something that the temperature is dropping towards room temperature. It's dropping faster in the beginning because the temperature differential is the biggest, right? But as it gets closer and closer to room temperature, it can't continue to lose the same amount because there's less to lose. So that actually does fall into exponential decay. So we can actually say you're kind of right. A pufferfish's expansion does follow some type of intuitive exponential rule. Okay, the less room it has to expand, the slower it's going to expand. Would that make sense? The closer it gets to its final inflatable size, the more slowly it's going to expand. That fits exponential decay. Okay, good job with the pufferfish. I think that works. What else grows rapidly? Mr. Peck said weeds before he left. He was talking about not like the community of weeds, but a weed plant. Like you come out one day and the weed plant is only 3 inches tall. You come out the next day and the weed plant is 8 inches tall. That's how we got to talking about bamboo, remember? Growing through a person. Ugh. Would that be exponential growth?
Yeah.
Based on the weed's height. The taller the weed is, the faster it grows vertically. Is that true?
No. The more nutrients it gets, the faster it grows. So, I like that.
Okay, so we're talking about the more nutrients it gets, we have to keep the same quantity. The more nutrients it gets, does that mean that it gains nutrients more quickly?
No.
See, that's not necessarily true, right? You have to keep the same thing. You can't change units. So the more nutrients that it has, does that mean it's gaining nutrients faster? Not necessarily, right? Or if you're talking about the height, the taller it is, the taller it's going to get. Is that true? The taller it is, the taller it's going to get?
Maybe.
Not necessarily, right? Not necessarily. But what if we talk about the spread of the weeds? The more weeds that you have, are the faster they're going to spread. Is that true? That's true. Why is that true? Because if you have more weeds out there, each of those individual weeds can be responsible for what? Repopulating new weeds. So population, you said the word population. That's a big one. Populations grow exponentially. That's one of the big main applications of exponential growth. Populations grow exponentially because we're talking about people, right? The more people you have, the more people you're going to get. Is that necessarily true? For the most part, it is, because you know what people do? They reproduce. And the more people you have out there reproducing, the more people you're going to get. And it doesn't have to be people. It can be populations of anything. It can be populations of elephants. It can be populations of bacteria. It can be populations of weeds. The more you have, the more you're going to get. Okay? Think about cell division. Y'all know mitosis, right? You have one cell. It splits into two. 2 then becomes 4. 4 becomes 8. 8 becomes 16. 16 becomes 32. What's happening every generation? Are you getting the same amount every generation? No. You're getting more and more each generation because you have more and more cells that are splitting. So that's population growth. So population is one of the main things that is exponential. Now, let's talk about another aspect of exponential growth. Remember I said polynomial growth also grows rapidly. But x to the fifth, like x to the third and x squared, passes through the origin, doesn't it? So if we're modeling populations according to x to the fifth, and we're coming out of the origin, that means that at time 0, we have how many people? 0. Is it possible to start reproducing from 0 to start with? No, it's impossible, right? You can't reproduce bacteria unless you have at least one bacteria. You can't reproduce cells unless you have at least one cell. You can't reproduce people unless you have at least one people. All right, 2 people, right? No, that's how that works, right? But there are some organisms that can reproduce by themselves, right? Asexual reproduction, budding and stuff like that, like planaria and stuff. So we can't start exponential growth from 0. That's another characteristic of exponential growth. There has to be a starting value. There has to be a starting value. And once you have a starting value, then, whoo, the more you have, the more you're going to get. So what else do you know exhibits that rule besides populations? The more you have, the more you get. Money. You hit the big 2. Money is the other one. Now we're not talking about like money to invest in other places, but that's true. The rich get richer, right? We're talking about money like in the bank. You put your money in the bank and it earns like a certain percentage. Let's say like a checking or savings account earns 5% a year. If you put $1 into a savings account at 5% a year, you come back a year later and you've earned 5% on that dollar, which is what? 25% of a dollar? Thank you. I tried to make it easy. 5% of $1 is the nickel. You came back a year later and you earned a nickel. Now, what did you do to earn that nickel? Nothing. You just waited a year. Do you deserve that nickel? Probably not, right? Probably not. But the bank's going to give it to you because you gave them $1 at 5%. Now, nickel's not much, right? No one's going to say, hey, I'm wealthy now, right? But what if you put in $100 and you come back a year later? How much are you going to get at 5%? $5. $5 is more than a nickel, right? So the more that I had $100 instead of $1, the more I got. Does that make sense? Because it's at a certain percentage. And a percentage of a bigger number is a bigger amount than a percentage at a smaller number. Are you with me so far? Okay. So now we can start thinking about what types of things or what types of situations are truly exponential. We just answered the question. Anything that grows by a constant percentage rate will be exponential. Anything that grows by a constant percentage rate will be exponential because the more you have, the more you get. And if we go back to cell division, those also doubled every cycle. So it's the same thing as saying something that increases by a certain scale factor every time. If something triples every generation or quintuples every generation, that's going to be exponential, right? If it quintuples, 5 times 1, you earn 5. 5 times 100, you earn 500. The more you have, the more you get. So anything that's a certain percentage or a certain scale factor is going to be exponential. Can exponential grow out of nothing?
No.
No, we have to have a starting value. Can polynomial grow out of nothing? Yes. If you go on and take statistics, one of the things you do in statistics is you look at data and you try to fit a mathematical model to the data so that you can use it to project out, forecast a little bit. Well, you have to know if that data fits a polynomial model or an exponential model. And one of the things that you do to see if it's exponential is, does it follow that rule? Does it double or triple or quintuple every cycle? Does it appear to follow a certain percentage growth? But the other thing that you look for is, hey, my data that I'm collecting, is it possible for it to grow out of nothing? And if it can't grow out of nothing, it's not going to be polynomial. Okay? It has to be exponential. Or it doesn't have to be. There are other things. It could be tangent growth, but that's kind of rare. Exponential is actually pretty common because lots of things that you may think about in life are related to percentages, right? Or scale factors. Those are all exponential. Okay, Cool. So the two big ones on example one that I'll write down are populations, populations, and money. I'm just going to, for money, I'm just going to switch to green and I'm going to put a cha-ching, a dollar sign. I like to put two lines through my dollar sign instead of just one line. Okay, populations and money. Those are the two big ones. All right, here's the formal definition now of an exponential, not the intuitive one. The intuitive one is the more you have, the more you get. It grows at a rate proportional to the current amount. Here's the formal definition of exponential growth. An exponential function is of the form f of x, there's the function notation, equals a, that's our vertical dilation factor from our standard transformation form, times b raised to the x power, a times b to the x power. So notice the first thing here. My variable x, which is my independent variable, it's no longer the base like it was in polynomials, right? X squared, x to the third, x to the fourth. The base was the variable. For exponential, the variable is now where? In the exponent. The variable is the exponent, right? Or it's in the exponent. And the number, which is b, we call that the base. We call b the base, where b is an element of the degree symbol. That should not be the degree symbol. That should be a real number. Let's change this degree symbol here to the double bar r. It's just a number, okay? So it's switched around. So x to the fifth is going to be polynomial. But if I flip that around and say 5 to the x, that's now exponential. You see the difference? We have a numeric base and we have a variable exponent instead of the other way around for polynomial. Now your base could be anything. As long as a is not 0, a can't be 0 because if a is 0, it wipes everything out. A is some non-zero number, but it's still your vertical dilation factor. B is called your base. It's either greater than 1 or it's between 0 and 1. Your base is either greater than 1 or between 0 and 1. If your base is greater than 1, we call this growth. If it's between 0 and 1, it decreases. We call it decay. Okay? If it's greater than 1, it's growth. I forgot the W there. That's why it looks funny. Groth. I wrote groth. Groth. Growth. And if it's between 0 and 1, it's decay. Now let's talk about A for a second here. A is still your vertical dilation factor, but it's also your initial value. Remember I said exponential has to have a seeding value. It's also your y-intercept of the graph, of the function. Watch this. If I plug in a 0 for x, that's how I find y-intercepts, isn't it? F of 0 is always the y-intercept. What do I get when I plug in a 0? I get a times b to the 0, and what's b to the 0? 1. So I get a times 1, which is a. A is your vertical dilation factor, but it's also your initial value. It's that value that you're starting with. Okay, whether it's $1 or $100 or 2 people, 2 cells, whatever, A is that starting value, and it's also then the y-intercept of the graph. It's where we start usually when we look forward into the positive x quadrant, the y-intercept. Okay. Now I said B has to be greater than 1 or between 0 and 1. There are other values of B, so let's just explore this. What would happen if B were actually equal to 1? In other words, if B were 1, the example would be, what would y equals 1 to the x power be? What's 1 to the first? 1. What's 1 to the second? 1. What's 1 to the fifth? 1. What's 1 to the negative first? 1 over 1. Yeah, which is 1, right? What's 1 to the negative second? 1 over 1 squared. 1 over 1 squared, which is still 1, right? What's 1 to the negative fifth? 1 over 1 to the fifth, which is still 1 over 1, which is 1. What is this always going to be? It's always equal to 1. Does 1 grow? No. Okay, so when the base is 1, this is just equal to 1. This is your horizontal line at y equals 1. It's not exponential growth. Can't have it. Okay? So what if the base is less than 0? What if the base is negative? Well, what if I have something like this? Negative 2 to the x power. This freaks out. this thing freaks out. Whenever you have a negative base, it freaks out. Watch this. What would y of 1 be? Well, that's negative 2 to the first power. That's negative 2. That's no big deal, right? But what if I do this? What if I do y to the 1/2 power? Now all of a sudden that's negative 2 to the 1/2 power. That's the square root of negative 2. Uh-oh. That's imaginary. Oh my gosh. We get imaginary numbers right there. So you can't have a negative base because the negative base will not give you the exponential curve that we're looking for. It gives you something that's it freaks out. If you try to graph it on your calculator, it's going to look very, very irregular. It'll have some real values and then there'll be like holes all over the place and it doesn't work. It doesn't give us the clean exponential growth that we're looking for. So that's why our B values, the base, which is what we call this, B is the base, it has to be either strictly between 0 and 1, like 1/2, 2/3, 0.5, whatever, in which case it's decay, or it's greater than 1, like 2, 3, 4, 5, 3/2, whatever, in which case it's growth. All right, that's the only two things it could be. All right, here are some examples. F of x equals 3 to the x. There's your exponential function. What's the base? The base is equal to 3, and the variable is, so would this be growth or decay? This is growth. Your scale factor is 3. This would be something that triples every generation. When I say every generation, I mean every integer value of 1. When x is 1, x is 2, x is 3, x is 4, we call those generations. Okay, this is going to triple every time. Times 3, times 3, times 3, times 3, times 3. It gets exponentially larger. There's one other key part of exponentials that I should probably add up here before we get further along. The domain is all real numbers of exponential functions. They are smooth and continuous for all real numbers.
How is that? So it goes into the -2?
Yeah, you want to look at that? Let's look at let's finish this off and then we'll look at it. 2 times 10 to the x. Is that the same as 20 to the x?
No.
No, it's not. It's 2 times 10 to the x. 2 is your initial value. 2 is your y-intercept. But what's the base? 10. Is this exponential growth or decay? It's exponential growth. Man, if your money grew like this, you'd like that. Every generation, it increased by a factor of 10. It goes from 100 to 1,000 to 10,000 to 100,000 to 1,000,000, very, very quickly growing, right? But it's not equal to 20 to the x. 2 is your initial value. 2 is your y-intercept. 2 is your seeding value, okay? So that would also be exponential growth. I'll just put a G underneath it for growth. G for growth. All right, what about this one? 4 times 1/2 to the x. Is this exponential? It is exponential. What's the base? 1/2. And the exponent is x. See that? That's how we know it's exponential. The variable is the exponent. The base is 1/2. And the seeding value, the initial value, the y-intercept is what? 4. Got it? 4 is the y-intercept. So this would be something that gets smaller by a factor of 2 each time. Smaller by a factor of 2. It's half of what it was. So it goes from 60 to 30 to 15 to 7.5 to whatever half of that is, right? It gets smaller and smaller and smaller and smaller by a factor of 2, which means it's half of what it was previously. Do y'all know anything from science that exhibits this type of growth where you talk about half of what it was, 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 half of what it was? You were about to say something before you blew your hair. No? Radioactive elements, has that come up in chemistry? Carbon-14, has that come up at all in chemistry? Oh my gosh, I'm sorry to hear that. Have you heard of half-lives? Half-lives. You measure radioactivity by half-lives. Half-lives is basically, it tells you how long it takes for a radioactive unstable element to lose half of its mass. It takes so many years or so many seconds or days or whatever to lose half of its mass. Carbon-14 is an unstable isotope of carbon-12. Carbon-14 loses half of its mass roughly every 5,700 years. So y'all have heard of carbon-14 dating?
Yeah, carbon.
Carbon dating. It's called carbon-14 dating. Yeah. This is where you find one carbon-14 molecule and another carbon-14 molecule, and then you hook them up and you send them out on a date, right? And then you observe them. Carbon-14 dating. And you look to see if the romance sparks or not. Is that what we're talking about when we say carbon-14 dating? No. We're dating an artifact usually by measuring how much carbon-14 it has compared to how much carbon-12 it has. You see, every living organism has carbon-12 in it. But every living organism that's affected by the sun also has carbon-14 in it. Now, the carbon-14 is constantly being regenerated as the animal is alive. The carbon-14 continues to be regenerated as the organism is alive. But once the organism ceases to exist, the carbon-14 is no longer replenished and it starts to decay exponentially. Every 5,700 years, it loses half of its mass. Well, the carbon-12 stays stable. So this is how scientists date artifacts. They measure how much carbon-12 it had, they compare it to how much carbon-14 it currently has, and they know that that difference then, excuse me, because carbon-14 decays every 5,700 years, they can approximate how old the artifact is by comparing the two levels of carbon-12 and carbon-14. So radioactive elements, half-lives, those are also exponential. Now, to talk about what happens then on the other side, let's look at y equals 1/2 to the x. What would be the y-intercept for this function right here? What's the initial value? If it's implied to be a... No, the initial value, the a value in front is, in other words, what's y to the 0? It's 1, right? So this passes through 0, 1.
Oh, that's
Yeah, and then at 1, it's at 1/2. At 1, it's at 1/2. And then at 2, it's at 1/4, right? It's at 1/4. And then at 3, it's at 1/8, right? And at 4, it's at 1/16. What's happening to these values? They're getting smaller and smaller and smaller. Now, will they ever equal 0? If you keep taking half of something that exists, will you ever reach 0?
no.
Never. This is why half-lives work. It doesn't matter how old the organism is. It could be a cajillion years old. As long as we have the instrumentation and the tools available to measure how much is left, we can approximate how old it is, because there will always be a trace amount left. You can never take something that exists and then keep taking half of it and get to 0. It will approach 0, right? It'll get smaller and smaller, approaching 0. What graphical phenomena do we have when something approaches a y value without actually reaching it? What do we call that? An asymptote. This function has a horizontal asymptote. A horizontal asymptote at y equals 0. Yeah, well, the equation itself is all real numbers, right? So like if I looked at y of -1, that would be 1/2 to the -1st, which is 2 to the 1st, which is 2. So that's going to be right here. If I put in a -2, y of -2 is going to be 1/2 to the -2nd, which is 4. So that's going to be up here. So what's happening is it continues on in this direction and it gets bigger. So the exponential decay function has a domain of all real numbers, from -infinity all the way to infinity. And this function would be a decreasing function, and decreasing means decay. Now, to answer your question, when we apply a mathematical equation to a real-life model, we have to look at a relevant domain. Okay? We do the same thing with parabolas. You remember from Algebra 2, where you had the guy hitting the golf ball, and the ball went up in the air, and it had to clear a tree, and then it came back down? We looked at that quadratic, inverted quadratic, we looked at it on a relevant domain from when he hit the ball to when the ball landed. But the equation of the graph means that it would keep going down into negative land below the graph, below the ground. Same thing here. when we apply a model like this to like radioactive decay, we only look at the values of t, time on the x-axis greater than or equal to 0. But that doesn't mean that the equation still doesn't have values over here in negative land. Okay? So the domain of every exponential function is all real numbers, but when we apply them to real life situations, we typically are looking for t greater than 0. So we're typically looking for values to the right of the y-axis. That's called the relevant domain, not the domain. Okay? So that's another feature of all exponential functions. Not only do they have a domain of all real numbers, but they all have a horizontal asymptote at y equals 0, affecting one end only. Okay? Affecting one end only. So on this one, on the decay, it's only affecting the graph on the right-hand side. On the left-hand side, the graph is increasing to infinity. Okay? The graph is increasing to infinity. What would it look like then? Let's look at this real quickly since we're right here. What if I looked at its counterpart 2 to the x? What would the y-intercept be? It would be 1 again, right? That's the point 0, 1. And then at 1, it would become 2. And at 2, it would become 4, so on and so forth. So this one is growing like this. But what if I looked at negative values? What would be 2 to the negative first? It would be 1/2, wouldn't it? Well, 1/2 would be right here. What would 2 to the negative second be? 1/4. What would 2 to the negative third be? 1/8. You see what's happening now? Now it looks like that. Do we still have a horizontal asymptote? We still do. But this would be an exponential growth function. And now on the right-hand side, for positive values of t, it's getting really, really big really fast instead of small really fast. And as we go out to the left, it's going to 0. So you can see that these two are related. In fact, if you were to graph these on the same coordinate plane, would you be able to get one from the other pretty easily? How?
By the inverse.
How would these graphs be related to each other if I graphed them on the same coordinate plane? They would have the same y-intercept, wouldn't they? 0, 1. They would have the same horizontal asymptote. Anybody? How could I get one from the other? This one at negative 2 has a y value of 4. This one over here at positive 2 has a y value of 4.
Find the inverse. Oh yeah, across the right. Y.
Across the y-axis. They appear to be reflections of each other across the y-axis. Guess what? They are. They don't just appear to be, they are. Guess how 1/3 to the x and 3 to the x are related to each other? They're reflections of each other across the y-axis. Guess how 4 to the x and 1/4 to the x are related to each other? They're reflections across the y-axis. Yeah. So how are the bases related? They're reciprocals of each other. So reciprocal bases are just reflections of each other across the y-axis. Okay, cool. Let's take a look at example 2. We want to identify equations now as exponential, which we'll call E, or not exponential. We're looking like this. This is what we're looking for. We're looking for the equation to be of the form some number times some base raised to the x power. Hang in there. All right, let's look at it. Example A. Exponential or not exponential? Exponential. Is it growth or decay? Growth. So I'm going to put EG for exponential growth. Are you okay with that? Exponential growth. The base is 7, which is greater than 1. The y-intercept is 1. The starting value is 1. And there's an x in the variable. So that's exponential growth. Okay. How about x to the 7th? This is actually what type of family of function? Polynomial, which grows pretty rapidly. But in the end, not as rapidly as exponential is going to grow. How about x to the x? It has the variable exponent, doesn't it? That's required for exponential. But what type of base does it have? Also a variable. This is like a hybrid, right? This is like a hybrid polynomial / exponential. Polynomials have variable bases. Exponentials have variable exponents. This is neither. This one is actually called an Aleph function from the first letter in the Hebrew alphabet. It actually grows faster than exponential. This is kind of the queen of all growth, or the king of all growth, however you want to look at it.
So instead of saying exponentially, you say
Alephly, right. Yeah, if something is growing faster than exponential, you say, man, this is growing alephly. You don't hear a lot of sports announcers using that, right? Yeah.
So will we be studying this one?
We will not be studying the Aleph function. We're just recognizing that it doesn't fit the form of a number raised to the variable power. I'm just telling you the name just to give you more info.
Did you learn it?
I had to talk about it, yeah, in my graduate studies. All right, let's look at this. There's implications too for computer programming with how fast functions grow. It's called the big O function. You don't want computer programs to grow too rapidly, too fast. They'll crash. Is this exponential?
No.
Well, let's see. What are the requirements? It has to have a variable base. A numeric base. Sorry, a numeric base. Does it have a numeric base? Yeah, and it has to have a variable in the exponent. Does it have a variable in the exponent? Yes. Ultimately, the true litmus test is, can I write it as a times b to the x? And that little +1, that +1 doesn't really do much. What does it do to the equation 15 to the x graphically?
Well, when you
It moves it to the left 1 unit. Very good. If you take 15 to the x and you reflect it across the x-axis, which is what the negative does, you vertically stretch it by a factor of 2, and you move it left 1, don't you still have an exponential graph? Yeah, you've just moved it to a different location. So as long as it has a numeric base and a variable in the exponent, it can have other parts of your standard transformation form, and it would be fine. It would be fine. So this one is actually good. This is exponential. Now, I'm not going to say it's exponential growth because the negative reflects it across the x-axis, which actually makes it a modified. It's actually decay. So I'm just going to say exponential. What about 4 times pi to the x?
Yeah.
Yes. What's the base? Is the base pi or 4 pi? Nope. It's just pi. What's your a value? 4. Okay. So you got to be careful. If I wanted the base to be 4 pi, it would have to be in parentheses like that. Is it in parentheses?
No.
No. So it's just pi is the base and x is the variable. So this is exponential. Now, because this is not a transformation, other than the vertical stretch by a factor of 4, which is your starting value, would this be growth or decay? Growth. Why? Because pi is bigger than 1. There you go. There you go. All right, we got a whole other row to go here. How about 3 times 1 to the x? Exponential or not exponential? It has a numeric base and a variable exponent. But what's the base? The base is 1. Can you have a base of 1 and be exponential? No, this is a poser. This guy's a poser exponential. He's trying to take the exponential look. 1 is a number raised to the variable power, but really, he's not growing at all, is he? He's just 1 times 1 times 1 times 1 times 1. This is another name for y equals 3. It's just the horizontal line y equals 3. Okay, it's a poser. What about f of x equals negative 3 to the x? Exponential, yes or no?
Yes.
no.
What would the base be? Would it be negative 3 or 3? It would be 3. And what's the a value? Negative 1. Very good. Would this now be exponential?
Yes.
Yes. Yes. You got to be careful. Your dear Aunt Sally would call this negative 3 times x. But if evaluating it, it would do 3 to the x first, right? Exponents come before multiplication, which is negative 1 times 3. Very, very, very careful. It is growth, but it's reflected across the x-axis, so it becomes decay. So I'm not going to put that. But it starts as exponential growth. The parent function is exponential growth, 3 to the x. Now, look at letter F. Is this exponential or no? This one is no, because the base is now negative 3. And notice how it's in parentheses. So a huge difference. This is the one that's going to freak out. You can have real numbers, then you can have imaginary numbers, and it doesn't follow the smooth, continuous pattern of exponential. All right, how about 0 to the x? What is 0 to any power? 0 to the first, 0 to the second? This is just 0. It's just 0. So again, the base is 0, and we can't have a base of 0. So this is another poser. This is your second poser. You're going to have 2 posers. 3 posers, actually. Any negative number to an x is a poser. If you have 1 to the x, it's a poser. If you have 0 to the x, it's a poser. It's not. Now, what about this one here?
You have to move the x to
If I move the x to the top, good, it becomes 3 times 4 to the x. Does that fit the mold? Yes. Now, remember when we did this with polynomials, we couldn't modify it and say that it was still a polynomial because we would have domain restrictions. And the domain has to be all real numbers. But guess what? When you move these exponential pieces around, you don't affect the domain. The domain is still all real numbers. In other words, I can write this as 3 times 1/4 to the negative x. That's another way to write it. Okay? So it fits the a times b to the x format. It actually works. Okay? So this is going to be exponential. It is exponential. And the parent function would be 1/4 to the x, which would be exponential decay. Okay, but the negative in front of the x reflects it across the y-axis. All right, cool. Let's try out evaluating with the calculator for a second here. Let's go to the calculator. Go ahead and just do what I do here. Let's go to the Minnesota calculator. This will be the last thing we do for the day. Minnesota calculator. And again, I have found that it's easier to get your third of a window first, and then go ahead and go to the graphing calculator, load the test, load question 1, and then go to the triple bar, and then go to the calculator, and then click on the double A and hit hide toolbar. And with a little bit of work like that, we have ourselves a handy-dandy TI-84, don't we? All right, now, to evaluate these at several values, here's what we're going to do. We're going to put it into Y1. So to do that, I'm going to type it in exactly as it shows. I'm going to do parentheses, and then alpha x. Y'all know the alpha x button? Alpha x gives you, see how it has the little box divided by a little box? That's your horizontal division bar. You want to get in the habit of typing it in with a horizontal division bar and not just a slash like Peyton did. Okay? So I'm going to type it in as a 1/3, click to the right, parentheses, and then caret to the x power. This is called math print. Does that match what's on my paper? Yeah, okay. Now I can go ahead and go to the home screen, and I can evaluate it. What's f of 2? Well, that's alpha trace number 1 of 2. And I get 1/9. Well, I could have done that one without the calculator, right? 1/3 squared. That's 1/3 times 1/3. That's 1/9. What about to the negative 3/4? Well, alpha trace of negative 3 divided by 4. I can do the slash there. That's 2.279. What's f of pi? Alpha trace enter of pi, which is second negative. Oops, I did e. It's second caret, sorry. You get 0.0317. And then f of the square root of 2, that's alpha trace y1 of the square root of 2. Oops, I want to delete that, go out, and then do that. Okay, so math print. Make sure you use math print to your advantage. How many decimals do we report? That's, I guess, what the point of this is. We report 3 decimals. Round or truncate. Either one. Round or truncate.
So in the pi 1,
Yeah,
is it 3 zeros after the
Oh, yeah, I did 3. Yeah, if you do more than 3, that's fine. It could be 031, 031, or 0.032. You can round or truncate. Yeah. I did 4 decimals. And hey, here's the deal. If you do more than 3 decimals, and they're the right decimals, that's okay as well. Okay, you can always do more than 3. 3 is the bare minimum, though, if it doesn't terminate prior to 3. So we'll stick with 3. All right, that's all we'll do for today. We got through example 3. We kind of talked about example 4 already, so we'll start with that tomorrow. All right, exponentials. They grow rapidly, don't they?
start with that Monday.
Oh, that's right. I'm coming without y'all tomorrow. That's going to be kind of weird teaching to an empty classroom tomorrow morning. But I'll record the video so y'all can watch it over the weekend.